at a bit of a different angle, which is that neural networks are not explainable. Why are they not explainable? Well, first, because a neural network makes this feature transformation. So you're transforming your input into a feature space, and then that feature space into another feature space, and that feature space into another feature space. And what those feature spaces mean is impossible to tell. So the best explainability you can hope for in a neural network is understand how the input layer, how each of the features gets transformed into the first feature. And then for the output layer, you can understand what does an input mean for a classification. Everything else in between is very hard to interpret. There have been some works that try to map a particular activation to a particular feature, but they're typically very, very expensive to compute, and they don't provide as much information. Okay? The other end of the spectrum is decision trees. So decision trees, they don't make hierarchical features, but they make hierarchical decisions. So if you have an input example, let's say that's the base of the tree. If this is a binary tree, you will have two decisions, and then each of these decisions are going to have another two sets of decisions, and then that is going to have another two sets of decisions, and so on. So 2, 2, 2, 2, and then again 2, 2, another 2, and another 2. So at this leaf, you're going to have a maximum probability for a given class. Let's call it class A, class B, class A, class C, class D, E, D, C. So you understand that here, so this leaf is discriminating between A and B. So if you're at this leaf, you can only be at A or B. If you're here, it's because you're A or C. If you're, so this first leaf is discriminating between A, B, and C. That leaf is discriminating between C and D. So by understanding this structure, you can also understand how the tree is making the decisions. By understanding how this decision is made, you can also see how each input is going to affect each output. In this paper, they're using a particular tree. Well, before we get there. So this seems very interesting for explainability, but the main problem that trees have is that they overfit. Why do they overfit? Because if you think that this is ABC, this is DEC, so DEC, this side of the tree is never going to see any example from A, because if it comes this way, it cannot possibly be A. So what happens is that generally, as you go further down the tree, each node is, and of course these nodes have trainable parameters, each node is experiencing a smaller and smaller proportion of the data. Okay? So what happens is that the deeper the tree is, the more it overfits. It has been proven that you can make it not overfit, but then your number of training examples has to be exponential to the number of to the depth of your tree. So you need an amount of data that most of the times is prohibitive. So what do? They propose, okay, let's use distillation, because this is capable of transferring generality from a cumbersome model into a less cumbersome model. Let's use it on a decision tree, because we can interpret the tree. So if we can improve the generalization capability of the tree without needing an exponentially large number of examples, then the tree becomes very useful. So they use a very particular kind of tree which helps them with this whole distillation. They call it hierarchical mixture of bigots. I don't know if anyone had heard of that before. I had never heard of that before. Then I realized that they introduced the term here. They don't say it's a new architecture, they just say, let's use mixture of bigots. It is actually a bit of a joke. You'll see in a second. So how is the tree structured? It's basically a sigmoid function. So the probability of going to the right branch is going to be sigmoid of your example set of weights. So here it's going to be weight 0 and a bias term. And that one is 1 minus the right, let's call it the probability of right here. Okay? So you either, if this sigmoid produces something larger than 0.5, you go to right branch, otherwise you go to this branch. That is repeated here, so here you have sigmoid of x, w1, well this is going to become a bit complex with the, they put it, so this is w, so leaf is upper index, so 0, 1, and then plus bias, 1, branch, whatever. So you see how it goes. And so once you get to the final leaf, you cannot use that because you might have, well, you will have a different number of classes. So this one is a softmax. So it's a softmax which they define. So they define it as a softmax, but they put a parameter here divided by the sum over k, where k is the number of classes of pi k. So this structure is called a hierarchical mixture of experts. In the paper that they cite in this paper, these weights are also updated when testing. So that's a mixture of experts. For this particular application, they leave the weights fixed on testing. So it's a mixture of bigots because they don't change their opinion. That's the joke. It took me a while to get it as well. So they call it a hierarchical mixture of bigots. So you train your tree, and then your weights are fixed. So you know the exact path that each example will take, because all these weights are already known. These weights are called filters, and by looking at the filter, you can tell what is discriminating the decisions in the tree, provided that your examples have some explainability. We'll see a bit more of that later. There is a bit of a trick. So the eternal trick with trees is that you have to make a big effort so they don't overfit. Because if they start overfitting, then even these weights are not going to work out, even distillation is not going to work out. So the first trick, the first regularization trick that they do is that they introduce what they call inverse temperature. So that one, instead of being just sigmoid, is going to be sigmoid of beta of all that. And same here, sigmoid of beta of all that. And so what this does is it makes the tree make hard decisions instead of soft decisions. Why? It's actually very simple. That is sigmoid of f, the sigmoid function is that, right? Well, that is 0.5. If you call this the soft area, so let's call this the soft decision area, where your activation is a bit low, so you don't know if the example actually belongs to one side or the other, except by that threshold. This is the soft decision area, and then here you can call it the hard decision area. So what beta is doing is that if an example falls here,